This is Professor Pelt, and this is Algebra 2, Chapter 6, Section 3. This is Part 3 of the video. So now we're going to find inverses starting on page 4. This is the function notation. So if I write it in equation notation, it's y equals 6 to the x. So that is the original function. That's just the function notation. My marker's messing up here. Function notation. That is the equation notation. Okay, so remember the first step to finding inverses is to flip the variables because you're undoing one function with another function. That other function we're switching the x and y values. So x equals 6 to the y gives us an equation format of the inverse. So we need to solve for y. So I need to get that y down from the exponent. So I'm going to do log base 6 of x in log base 6 of 6 to the y. So why did I choose to do that? So what you do to one side of the equation, you must do to the other based on properties of equality. And why log base 6 of the infinite number of logs possible? Because that'll cancel what I have over there, leaving me with log base 6 equals y. So that gives me f prime of x, or f negative 1 of x equals log base 6 of x. So remember, the negative 1 exponent is the symbolization for inverse, which will be used in trig and calculus in the coming years, and starting here. Okay, so let's try one more. So they gave us the equation format. This is the function format, would be the natural log of x plus 3. But we need, so that is the original. So to get the inverse equation, switch the variables. So x equals the natural log of x plus 3. So we need to get rid of the natural log. How do we do that? With a base e, because natural log is log of base e. So that'll cancel. Then with e to the x, oops, I'm sorry, that's supposed to be a y. I don't know, I was supposed to switch the variables and I didn't do it. Okay, so that leaves me with a y plus 3. So I'll subtract 3. So e to the x minus 3 equals y. So the actual inverse is f negative 1 of x equals e to the x minus 3. So that is the inverse function. In the proper function notation, right? So that is the inverse function. Okay, pause the video, try the student problems. Okay, student problems. So we have the inverse, we have the original function. So the original equation is y equals 4 to the x. That is the original. To get the inverse equation, switch the variable. So x equals 4 to the y. So you need to get that y all by itself. So you need to get rid of the 4. So we'll do log base 4 to both sides using properties of equality. And we choose base 4 because that'll cancel what we want there. Leave me with log base 4 of x equals y. Oh, I wrote x there for some reason. I don't know why. Habit. Okay, so therefore, f negative 1 of x, or f inverse of x, equals log base 4 of x. So that is the inverse function. So we're basically just showing that the power equation, the inverse is the log, and vice versa. That's what we're showing. Okay, so that the function notation of this would be log of x plus 2. So this is common log, since there's no base specified, so it must be base 10. So that is the original. So get the inverse equation, switch the variable. So x equals log of y plus 2. So you must do, when there's multiple operations, in order of operations. So when solving, add subtract comes first. So x minus 2 equals log of y. Then we need to get rid of the log, but since it's a common log of 10, base 10, I need to do base 10 to both sides. So that'll cancel. Maybe with 10 to the x minus 2 equals y. So our inverse function, f negative 1 of x, or f inverse of x, equals 10 to the x minus 2. Okay, and you can see log to exponent, exponent to log. They're inverse of each other. We're just proving that basically. Okay, so prior we did some of these log evaluations by hand, and we figured out what they were. They were nice fractions and whole numbers, but that is not always the case. So if we try to do this one, it equals some value. 6 to some value equals 12 if I convert the format. Well, 6 to the 1 is 6, 6 to 2 is 36, right? 6 to the 1 is 6, 6 to the 2 is 36. So this must be in here somewhere, right? So it's going to be some decimal value, and it actually works out to 1.387. So you need to be able to use your calculus. The point of this is test out and verify your values match mine. You don't know how to use your calculator. All of the problems that don't work out to nice perfect whole numbers, you're not going to be able to do. Okay? So if you have a nice log button like I do, you can just put your 6 in there and your 12, and you will get a decimal value. You have to round it appropriately. If you have one of the old ones that only has common log, you might have to do log of 12 divided by log of 6. So if you have one that doesn't have a base option, you might have to do that, which is called base conversion formula, which you'll get to the same answer. You can use base 10 as your default if you only have a common log type button. Okay. So if there's no base specified, you might remember it is base 10. So if it is base 10, then you can just use your log key when you get 1.398. And natural log, you don't have to do log base e. Okay. You don't need to do that. Just find the natural log button. That works out to about 2.79. Okay. All right, we can verify that actually works. So there's my natural log button. We said what, 8? And if you do your log base E, whoops, you get the same answer. Okay. All right, pause the video, try the student problems for yourself. All right, student problems, if you did them correctly, you should get negative 1.585 approximately 0.653, and approximately 3.723. So the idea here is if you're not getting these values, you should seek help when using your calculator, because other than the whole number ones, you're going to have a problem if you don't verify how to do them properly with a calculator.